Hello everyone, welcome to problem 4.34 of Taylor's Classical Mechanics. So this one's going to be a fun problem. We have a classic situation where we have a one-dimensional system that is a pendulum consisting of a point mass m fixed to the end of a massless rod of length L and whose other end is pivoted from the ceiling to let it swing freely in the vertical plane. The pendulum's position can be specified by an angle phi from the equilibrium position. So the equilibrium position is, of course, if the mass is just sitting here in the center. It could equally be specified by some distance s from the equilibrium, but the angle is more convenient. We want to prove that the pendulum's potential energy is, in terms of this angle phi, is given by this expression. Then we want to write down the total energy as a function of phi and phi dot. Then we want to show that by differentiating this expression for E with respect to t, we can get the equation for motion of phi and show that the equation of motion is just the familiar torque is equal to I alpha, right? Where torque is equal to the moment of inertia times the angular acceleration, which is just the angular version of Newton's second law. Then assuming that the angle remains small throughout the motion, we can solve for phi of t and show that the motion is periodic with a period of 2 pi times the square root of L over g. I think that's it. Yeah. So let's take a look at this problem. I kind of drew out the situation here. So we have a pendulum of length L with a mass attached to the end. We have this angle phi here. And then I'm defining this distance to the equilibrium position as h. So if the mass was at the equilibrium position, this total length here would be h. However, when the mass is at the equilibrium position, phi is 0, right? So h is just equivalent to L, right? When we're at this position, the equilibrium position, h and L are the same, right? So that's just a relation. But also noting that h changes, like as this rises, h is no longer so h is not the length when it's at the equilibrium position. It's just the length of this side of this triangle as the mass changes height. So it's really just the vertical height component of the mass from the top of the ceiling here. And we can use a trig relation that the cosine of this angle is h over L, right? That means h can be defined as L times cosine of phi. And I just noted here again that when the mass is at here, when phi is 0, then h is L, right? When you plug in 0, cosine of 0 is 1, you just get h is equal to L. Now, I also noted here that I drew, this dotted portion is, as if the mass were at the equilibrium position, it would be here. But the mass is actually swung quite high up here. And so we know, and this is that angle phi here, we know that this side of the triangle, this part here, not the whole thing, but just this part is L cosine phi. This is our h. But the remaining distance here, we know that the total distance would be L if it was at the equilibrium position, but this remaining distance is still unknown. But this is just L minus this. So this distance here that's remaining, this is the distance that the mass is from its equilibrium point, which is what we need to know to define a potential energy function. It's just L, the total height, minus this portion of the height, L cosine phi. So then we can define the potential energy as a function of phi, which is mgh, which is going to be equal to mg times L minus L cosine phi. So really, I guess I don't know if h is really the best variable here because I used h up there for here. So I'm just going to real quick say that this is like y. I don't know. So this is y. So y is L minus L cosine phi, right? It's the height above the equilibrium point, which is what we need to know for the potential energy. And then we can factor out L to get mgL times 1 minus cosine phi, which is what the book wanted us to find. So it says here that it wants us to show that the potential as a function of phi is mgL times 1 minus cosine phi, which is what we just found here. Then what we can do is take the, we can figure out what the total energy is of the system. So the kinetic energy, of course, is 1/2 mv squared, plus this potential energy, which is mgL times 1 minus cosine phi. Well, if we want to get this whole energy in terms of phi, v is the linear velocity of the mass, the ball, which we know is related to the angular velocity by L times omega, where omega is the angular velocity, and omega we can just write as phi dot. So the linear velocity v is equal to L phi dot. So we can plug that into our kinetic energy to get 1/2 mL squared phi dot squared plus mgL times 1 minus cosine phi. And that is our energy in terms of phi and phi dot. So I'm just going to kind of circle that here. Then for part B, we can take the derivative of the energy with respect to time and get 1/2 mL squared. We get 2 phi dot, and then we got to take the chain rule, so we get phi double dot. Then we get plus 1 plus mgL. So this first term will go to 0 because this first term doesn't depend on phi, but we get the minus here. But then the derivative of cosine of phi is minus sine of phi, so we end up getting a plus sign. We get mgL sine phi. Then we got to chain rule that, so we get phi dot. And that's all equal to 0. Since all forces are conservative, then we can, so energy is conserved. Then we can say that dE by dt is mL squared. The 2's cancel, phi dot, phi double dot, plus mgL sine phi, phi dot. And then we can get, equate terms on both sides, and we can cancel terms. So right now we're just going to cancel the phi dots, and we're just going to get mL squared phi double dot plus mgL sine phi is equal to 0. We're going to keep the constants around because we need them to get this into the right expression. And then we can move one of the terms over, so we get mL squared phi double dot is equal to minus mgL sine phi. Now, the moment of inertia for a point mass like this is just on the end of a rod like this is just mL squared. So mL squared is I. And then phi double dot, that's just the angular acceleration. So that's alpha. So this left side of the equation is I alpha. And then the right side of the equation, mgL sine of phi, is just the force times the distance. So L is the distance. It's torque, right? So L is the distance. And then mg sine phi, that's just the component of the force in the vertical direction. So that's the component of gravity in the vertical direction. So this is just the force times the distance times the length of the rod. So that's just the torque. So what we found here then is just the torque is equal to I omega, which is exactly what we were trying to find. So this expression is just the same as saying that the torque is equal to I omega, or sorry, I alpha. And then we have that, assuming a small displacement phi, we can use, if you Taylor expand sine of phi about 0, and assuming a small phi, what you can approximate that sine of phi is approximately equal to phi. For small angles, this is just a simple small angle approximation of sine. So then what we can do is say mL squared phi double dot is equal to minus mgL sine of phi which is approximately equal to minus mgl phi, right? Plugging in phi for sine of phi. And what we get here is that we get a differential equation in terms of phi. So we get L phi double dot is equal to minus G phi dot, or moving terms of both sides, we get L phi double dot of t plus G phi of t equals 0. And this is a second order, constant coefficient, linear, homogeneous, ordinary differential equation. So just kind of classifying this differential equation here in case you want to go through and really solve it yourself. But you can solve this by assuming a solution in the form of e to the RT. That means the derivative is r e to the RT, and phi double dot is r squared e to the RT, because the derivative of e to the x is just e to the x, except we have a constant in the numerators, or in the exponent, so we have to bring it down. Anyways, plugging in this into our differential equation, we'll get L r squared e to the RT plus G e to the RT, which means, and this is all equal to 0, so the only way that this could be 0 is if this term in parentheses is 0, L r squared plus G, because the exponential function e to the RT will never be 0. That means L r squared plus G is 0. Solving for r, we get that r is equal to plus or minus the square root of G minus G over L, which is plus or minus I times the square root of G over L. So we get these two complex roots, and that gives us two linearly independent solutions. So phi can be expressed as this constant C1 times e to the I omega t plus C2 times e to the minus I omega t, where I'm defining omega to be the square root of G over L. And then I'm not going to do all the math here, but you can use Euler's formula to express e to the I omega t and e to the minus omega t in terms of cosine and sine, because we know e to the I theta is equal to cosine of phi, or e to the I phi is equal to cosine of phi plus I sine of phi. So using Euler's formula, you can rearrange this solution in terms of cosines and sines. And what you end up getting is that phi of t is equal to a times cosine omega t plus b times sine omega t, where a and b are constants. And omega, again, is just the square root of G over L, which we got from up here. So we used omega so we don't have to write this out every time. So that is the position, and this just shows us that the position of the pendulum is going to be this sort of oscillating function, right? It's sines and cosines, so it's definitely going to be some kind of oscillating function. And we can show that this is going to have a period, t naught. Sines and cosines, they repeat every 2 pi, so that means omega t, like the period t naught is going to be when omega t is equal to 2 pi. So solving for t naught is just going to be 2 pi over omega, or 2 pi times the square root of L over G, just flipping those around. So the period of oscillation of the pendulum is going to be this, where it's 2 pi times the square root of L over G. So the period depends on the length of the rod, and that's really it. All right, that wraps it up for problem 2.34. If you guys have, 34. If you guys have any questions, comments, or concerns, please feel free to let me know in the comments below. I'd be glad to answer them. And if you guys want to support the channel, feel free to leave a like, comment, subscribe. You can use the Patreon link to get access to these written solutions, as well as if you just want to donate, you can do so by using the Buy Me a Coffee link. So thank you guys for watching, and I'll see you guys on the next one.